Okay. Good afternoon, everyone, and welcome to this week's Kent Seminar Lecture. Today, we are very delighted to have Professor Alexandre Alahi as our speaker. Professor Alahi is an associate professor at l'École Polytechnique Fédérale de Lausanne, or EPFL, in Switzerland, where he leads the Visual Intelligence for Transportation Laboratory. Before joining EPFL in 2017, he was a postdoctoral researcher and a research scientist at Stanford University. His research focuses on socially aware artificial intelligence, where he combines computer vision, machine learning, and robotics and applies that to transportation and mobility. His research enables systems to detect, track, and predict human motion dynamics at all scales. In 2022 and 2023, Professor Alahi was recognized as one of the top 100 most influential scholars in computer vision over the past 10 years. Everyone, please join me in welcoming Professor Alahi to the seminar.
Thank you. Thank you very much. Thank you for the introduction. Thank you for having me. It's a great honor to give this remote presentation. I'm gonna start right away. So the title today is How Does AI Fuel Transportation? And potentially vice versa, how transportation will help AI. So first, how AI will help transportation. I think it's quite clear. We have all these known application of autonomous mobility. So AI is posed to make vehicles autonomous, such as self-driving cars, self-driving trucks, buses, trains, maybe delivery robots, ships, potentially drone, and so on. The motivation is also quite clear. It's to save life, to reduce human error due to accident, to potentially, by reducing accident, you have also a more sustainable planet, and so on and so on. First, I want to talk about the AI itself. Do we have the AI to make all these applications a reality? Let's look at one example of a self-driving car operating in the US. Usually, the common AI pipeline, I would say, again, sorry. I apologize. Another one, no. Is so the first step of the AI pipeline is perception, usually. So you have sensors, obviously, you have maybe cameras. The second one came. You have cameras, extract images, or maybe LiDARs, more fancy sensors. And then from these signals, you want to better understand the world, extract, potentially detect everything, put a semantic to it. And then, according to what you understood from the world, what you extracted, you are planning a path accordingly to follow your goal. And for many years, we really struggle to do detection, to really detect every object, and we're developing a lot of methods based in computer vision to really solve this problem. But nowadays, detection is really impressive. It's working, but we still have accidents, and we don't have self-driving cars in our street. And I'm sharing one here scenario where if you look at this pedestrian, and I'm going to ask you, what do you think the pedestrian will do in the next seconds? In fact, in this case, he decided to jaywalk to catch the bus. So AI in this situation failed to deal with this rare event. And the person monitoring the autonomous vehicle predicted this behavior and decided to intervene and brake. Otherwise, we'll have a collision. So what was missing in this AI pipeline? Another pillar, which I like to call social forecasting, or a prediction pillar, that is in charge of learning to predict human behavior, human interactions. And then the planning will also consider prediction to make a decision. But now, to better predict, we also need to maybe rethink how we want to, what we want to extract and perceive from the surrounding of a vehicle. And again, traditional autonomous vehicle treats human and object as only a point in space or a trajectory in time. However, we are much more than that. We consciously and subconsciously exhibit signals to communicate our intentions. So I claim that autonomous vehicle must detect these signals, such as human body pose, the focus of attention, our gestures, our action, and so on. So if we want to better predict, we need to also rethink perception and potentially do much more than just detecting people with bounding box or cuboid. And this is also true for other type of autonomous systems that are in charge of moving around, navigating the space. And if we look at this robot here, this is the view from the robot, and the robot potentially needs to navigate this crowded scene as good as human, and it's not that easy. So the pillars of this robot are also the same one. So you can suppose that you have a detection step that detects everything, and then the planning, it will look at what is physically possible given the detections. But looking at what is physically possible and taking the shortest path is not good enough, because we know that even if there is enough space between these two people, it's socially not accepted to go in between, and the person on the left is walking, and we can predict that we will intersect with them. So we should only take the right path, but that is thanks to our prediction capability of understanding and predicting what these people will do and what are these social norms that people like to respect. So to be able to do this, AI must read humans and understand their behavior. And our social forecasting pillar will address that. And if you combine it with perception and planning, you have what we call socially aware AI. So over the past decade now in our lab, we've tried to basically advance each of these pillars, and we shared independent libraries for each of them, open source to be fully transparent, to contribute to the field. Um, but then, if you follow a bit the field of autonomous driving, or even in the industry, you do have another paradigm, which is potentially solving exactly the same task, but in an end-to-end fashion. What does it mean is that you have your image of a camera or from your LiDAR, and you only have one step, which is tell me what should be the control, what should be the planning, and you don't have these modular steps. Um, why we are interested in this modular step? They have one of the motivation is each of these modular step has also its own application in other domains. So you can, if you develop algorithms to solve each of them, take these algorithms and solve other problems. For instance, you can here do autonomous robot, but you can use exactly the same pillar to do autonomous, vehicles, as we saw initially, but also other type of applications such as autonomous cities. For instance, when you want to automate a city by controlling their traffic light to reduce congestion, which is also a key problem, you can follow these steps. The first step is perception, which is understanding the current state of the city. You can use drones or other type of cameras that are installed in the city, and these cameras can detect vehicles, understand the current state of the city. Then the social forecasting will predict where these vehicles will want to go, they will go, and based on this prediction, plan or act or control the traffic light in a way that you will reduce congestion. So if we develop all these different tools and methodologies, we can apply it to different type of application. And I'm going to share another application, which is still related to mobility, which is uh, developing autonomous bodies for humans who are actually paralyzed, who cannot walk again. And I'm going to show you that we can use exactly the same type of pillars with the same methodology to do that. So how we do that, for instance, that if you have a patient that is paralyzed, you can have a robot that will look at the patient with its camera, detect the skeleton of the patient, the state of the patient, the current state, has the capability to predict what should be the next state, the next skeleton, the next pose, and that's the social forecasting step. And then control the muscles of the patient by sending electrical stimulations to them so that the body will match the desired predicted set of skeletons. So this is an illustration here. You have our robot on the left, look at the patient, detect the skeleton, knows what should be the next skeleton. So hence will control some electrical stimulation in the body of the patient to make the patient walk again and do the right gesture. It is a feedback loop. So why am I'm sharing this also application is again to tell you that if we have robust method to solve each of these step, we can really extend their application to just more than potentially self-driving car. And when we do that, at the end, it's all about learning good representation from the data. So we can look a bit of the challenges. For each of these pillars, we like to frame them as a deep learning task where you have some input and some output, and you want to potentially learn a latent representation with a neural network that will make that task robust to a lot of factors of perturbations. So in the context of perception, what we want to do is we have an image and we want then to be able to detect or understand the current state, but we want to, for instance, detect the pose, the action, the focus of action. And the traditional way to do that with deep learning was for every task, you have an independent network. But because we're interested in real time and efficiency, and potentially have small amount of parameters that we need to embed maybe in a device or on board, we are looking at how can we have a single network that will actually solve all these perception tasks in a feed-forward way. So we have been looking at this for many years, and there are a few. So our motivation is how can we learn a shared representation to read that reads human in general. And when you do that, if you naively, for instance, take a neural network and add multiple heads for every task and multiple loss functions, so you can actually combine your loss functions and then backprop, update your backbone, you lose performance for each of these tasks. Some of these tasks have more data, or they are not actually, they are competing with each other. And this concept of multitask learning is not that trivial. So what we have shared in this paper that I'm sharing here is we need to be very careful in how we backprop the gradient that comes from all these loss, and we can be smart about it by rethinking how we normalize the gradient for each of these loss and where in the network. So usually our network are based on a backbone and some head layers, and the way we will normalize for the head layers will be different than for the backbone. And so we show that by rethinking this normalization, we can actually do a good job in not losing performance when we combine all the tasks. But then there are also other things that we discover over the years, which are follow-up work, which is when you have multiple data sets, because sometimes each of these tasks have different data sets with different set of labels that are available. So you don't have a single data set where all the perception tasks have been labeled. So the community has usually focused on different perception tasks for different data sets. So when you do multiple data set training for the same network, there's this concept of a batch normalization of your batch, batch norm, that has actually a negative impact if you use multiple data sets, because these data sets have different distribution, and the parameters that you update or keep with between each batch are affected by which data set you're actually loading in the batch. So there have been other type of normalization over the years, such as layer norm with different architecture, that if you are doing multi-task, we have shown that they are the type of normalization that you should use. But there are also other things that we will help to address this problem. Another one is rethinking your augmentation. As I said, some of these tasks, they don't have the same number of examples. So we showed that if you think carefully about augmentation and do advanced type of augmentation with generative AI, for instance, all these image generation, conditional image generation, well, especially for the task where you have limited number of example, it actually gives you a huge boost. But if you have large enough, it doesn't necessarily help. And finally, this transformer architecture based on attention mechanism, cross attention, self attention. In this context, also, if you look at them and add this cross attention in this head network across all these tasks, will give you potentially a boost to not be penalized by doing these multitasking. So these are the few key messages that we learned over the years on learning the shared representation. Here are some qualitative results. So our goal is really, given an image, for instance, being able to extract the skeleton of humans, of vehicles, of animals, of bicycles, and so on. So here are some videos illustrating that. It's a bit of a long video, but if you're interested to use this type of models, we have a live demo online, which I'm sharing here. And we have open source libraries for extracting all the skeletons of all kind of objects that you're interested, from a vehicle, human, animal, hand, even furnitures. So we have a lot of list of semantics that we show, even lanes. So we showed that, in a context of self-driving or autonomous driving, you're interested in detecting the lanes, and you can frame them still as a key point detector, as a skeleton task, estimation task, and it's competitive with state of the art. Then suppose that we have extracted this skeleton. What can we do? We showed that extracting skeleton, even on all type of objects, is a very interesting intermediate representation for other tasks, other perception tasks, such as understanding the 3D. So we show that given a single camera or a single image, which is, has no information on depth, if you extract the skeleton of your humans in 2D, in the image plane, we can actually infer how far they are to the camera. We can actually infer the 3D. We can infer their action and activity, and potentially their intention, for instance, to cross the street or not, which is state of the art, or other methods usually use the whole image to solve this problem. But we show that with skeleton as input, we are in fact outperforming previous work as well. These are some qualitative example. Here, in the top, these numbers that you see are actually how far we estimate this pedestrian to be to the camera. So it's a measure of depth. And in the bottom, we illustrate this also in 3D. What is our method estimating respect to the 3D, using only skeletons as input to solve this problem. And this is another qualitative illustration of the capability of our method to predict the intention of humans to cross the street or not. Again, given the skeletons, we are able to correlate this skeleton with crossing behaviors, like predicting and the fact that these people will cross. So this is what we have been doing on perception. But one thing that I want to share is that still there are still challenges and limitations. And we still need to do a lot of research to solve this problem of rare event detection or action detection. Um, we're doing a pretty good job if we have enough examples of what we want to perceive. But in practice, there will be a lot of scenarios that we will not have enough examples in our training data, or we didn't even collect data on this type of observations. A weird object that we never labeled in our data, a surprising interaction, a surprising activity that we never thought about it. How can we actually perceive this even if we don't have a lot of examples for them? So this is what we are currently working as ongoing research, and I'm going to share a few ideas on how to do that later. Then for our second module, predicting, it's really a sequence-to-sequence prediction problem. The simplest version is you have coordinate of humans or vehicles in the space, so spatial temporal data, and you want to predict where they will go. You observe 2 seconds, and you want to predict where they will go in the next 4 seconds. You can even look at it as a time series prediction. But if you look at it as this sequence, your state can be of any dimensionality. So a long time ago, we proposed one of the, I think, to the best of our knowledge, the first deep learning method that will solve this forecasting task in an end-to-end manner with LSTM back then. We called that social STM and social GAN. Social STM was kind of deterministic, and social GAN was outputting a multimodal distribution, multiple trajectories. And then over the now past decade almost, there were an enormous race of methodology improving on this end-to-end method for that specific task. And even ourselves, we suggested methods to ease the transfer. So for instance, if you have trained a network that is able to do a good job on humans, on predicting human trajectory, and now you want to predict bicycles trajectory, should you retrain from scratch, fine tune, or just slightly adapt your network with some smart mechanism to solve the prediction of bicycles dynamic? And we show that, yes, if you follow the same philosophy as in NLP, in NLP, there is this concept of a LoRa, where you have a very expensive network and you just add a few parameters with some constraint on the low rank of these of the path of the set of parameters. Well, you can then modify the capability of the network, and this will outperform fine tuning, for instance, over some layers. So we show that we can do that also in this context. That we can use these recent diffusion models that are also a new paradigm to do generative AI, to do generation. And finally, a more flexible formulation where we claim that we can use coordinates, but also other cues such as the skeleton or other semantic on the humans to better predict where they will go. So by also considering the skeletons as input, we can improve the accuracy of our prediction. But again, there are always but. What is left for us to do? We realize and we notice that all this end-to-end formulation depends a lot on the data, on distribution, and sometimes even basic behaviors are not learned because they were not necessarily available in the training data, and they could fail in being predicted. So how can we also address this issue of being able to predict all the behaviors, but even some basic ones, and not be having adversarial behavior in some very simple cases? And we have another paper proving that many state-of-the-art, for instance, vehicle trajectory prediction, because there are these online benchmark, are actually not robust to very simple road changes and interactions. although they rank first in public challenges and they beat everybody, they have amazing numbers. But then when you test them on basic interactions, suddenly they output unrealistic behaviors. So that's what's left to do in this module. The last one, planning, is a bit similar to prediction, but now you have a goal, so you want to predict how to reach your goal. This is commonly addressed with in a reinforcement learning framework, especially in the context of robotic. And what we showed that is that you can improve the supervision of this model by rethinking positive and negative behaviors. So usually in your data, even if you collect data from human interaction, you are observing positive behaviors. Um, and in machine learning, when you do have the contrast of positive and negative behavior, your learning is much more powerful. So how can we simulate negative behaviors? By synthesizing them and using a smart way to suggest wrong behavior, but artificially, so that the model can better understand that, for instance, a collision is bad. We don't want a collision, and have it as an example that it should avoid. And you can do this with contrastive loss, and we have more details in these publications. But yet, when you do planning and when you do this simulation, you still suffer from distributional shift. The world is the reality is way different than your simulation. So whatever you learn in simulation or by generating synthetically does not necessarily always transfer to the reality. So how can we address the shift in distribution? So this is the challenges. So we have about all these challenges that we need to solve for each of these pillars. And then I ask myself, okay, now that we have identified all these challenges, thanks to this application, and in fact, thanks to transportation and mobility, how can we rethink all these, our paradigm of learning representations? And how can we improve that? So I came up with, I'm suggesting a few principles that could help us address all these challenges and all the that are still true nowadays. So the color code is potentially helping to address each of these challenge, and I'm going to share a few. So the first principle that I believe will help us learn better representation to solve our task. And the first two are the principle of prediction and the principle of opposites. What does it mean? It means that when you look at the current success story of representation learning, one of them is, ChatGPT in NLP. They are based on this concept that a representation that learns to predict sensor input response is a powerful representation to learn other tasks. So this idea is not new. It goes back to 1860. There is this. There are these neuroscientists that argue that our brain actively makes prediction about the world based on past experience. And this is what foundation models are also about these days. This generative pre-trained transformer, they learn a representation to predict your signal in a context of NLP text. They learn to predict what's the next word that should come if you give me a set of word. And then once they have learned to predict what is the next word in a self-supervised manner, so we have a lot of signals, right? We have a lot of text. We might have a lot of images. We can learn to predict the next image in a video. Then these models are fine-tuned with specific tasks and data based on the principle of opposites. And what is this principle of opposite? It means that learning is successful by means of opposite through the contrast of positive and negative example. As Rumi said, Things are known by their opposite, light by way of darkness, and so on and so on. So I believe that a representation learning paradigm can be staged as two steps. First, you have your neural network that learns to predict anything on unlimited amount of data. So any signals that you have, you can frame it, just learn to predict that signal in time. And then the second stage is learn specific things, specific tasks with much less examples, but positive and negative examples. And then maybe with just few example, you can actually learn these rare actions, these rare events. And again, this is currently the current trend of AI. In text, you have these foundation models, Gemini, GPT, many nowadays, DeepSeek, and so on. But then you can take them and fine tune on some of your specific data, tasks for specific purposes. It can be summarization, sentiment analysis, whatever you want, but then you share a few examples and it's able to do that task. And it's usually much stronger, much more performant than just focusing on your end task and using just the end task data to learn to do it. And we have actually some ongoing project on this. We wanted to see how we can basically use this principle in the context of, for instance, perception. Can I improve perception by first having a self-supervised step? What is my self-supervised step? I can say I have an image that I extract. Can I actually generate what should be the next frames that will come after my image? So I can do image to video. So this is also a very popular field in generative AI. You see online every day image generation, video generation given a prompt, and sometimes video generation given an image, a starting point. So this is what we have worked on. You can also look at it as a word model. A word model is basically a model that forecasts, given some input, some observation, will forecast the future, right? So in this context here, you have as input maybe an image coming from a car, from a drone, or from Google Glass or HoloLens, and you want to predict what should be the next frames, what will be the next frames. And what you see on the right is actually the output of our prediction. So given what's on the left, we are actually generating what you see on the right. And you can also provide some actions. You can say, I want to go straight, I want to go left, I want maybe this object to move this way. Can you generate how the world should look like given this set of controls and action? And so we started to do this. We are not the only people who are working on this topic. Our competitors are actually usually the industry, big players with a lot of resources. And in January, NVIDIA shared this line of this work where, given an image, they generate the videos. They call this a word foundation model. And I'm sharing with you the amount of resources and compute they use. So they use 20 million of hours of video. They use 10,000 GPUs for 3 months to train their model, and they have a few models with 14 billion parameters. And their inference time, so when you use their model, you have to usually wait 10 minutes to get these videos from event frame. We are in university, we are not NVIDIA, we don't have the same resources. So we try our best, but we succeeded to have competitive result. We only used 4,000 hours, which is still huge for us because it represents a lot of data. But we took YouTube videos of driving, of egocentric videos. We had access to, which is still a lot, but nothing compared to NVIDIA, of 500 GPUs for 3 days. And then we trained our model that is a 2 billion parameter model. and our inference time is 3 times faster. But we also contributed on the methodology by providing much more controls on the data generation and showing that we can actually do a very good job in controlling the content in a fine-grained manner. I'm going to share some illustration. We based our work on the stable diffusion architecture. It's a quite famous model to do generative AI. So we have our input and then some controls, for instance, on if we want to move objects, if we want to move skeletons, how we should encode it into our stable diffusion architecture and generate the data. But what was also challenging for us is all these controls of I want to maybe generate my video with this type of skeleton, or using depth data, or even egocentric control, knowing the controls of my vehicle. When you look at YouTube, you don't have these labels. You have 0 labels, you only have images. So we took the bet of generating all these labels using algorithms. So we call this pseudo labeling. They are noisy, they are not perfect, but we wanted to still get these controls, these modalities, and show that if we have them as an input, we can actually generate realistic content that will follow these controls. This is an illustration of our estimated depth, our estimated skeletons, and on the right bottom is the ego trajectory of the vehicle, which could be obtained with a GPS or things like that, but we didn't have that, so we had to estimate it given the images. But putting everything together, we were quite happy because we're able to actually generate these videos. So on the left, you have this image, and then on the right, you see what we generate given different type of controls. For instance, turning right, turning left. This is very useful for simulation. So if you want to simulate rare events, we have this capability to do that. If you want to use this as data augmentation, we can do that. If you want to train a planning algorithm, you can use this as a word model to do your planning, to evaluate your policy. So potentially its impact can be quite broad. And then this is another illustration. You have the image on the left. We show how we can generate a video that a behavior that turns right and a behavior that turns left. And something that we do that NVIDIA and our competitors at that time were not doing is we can control the content. So we can say, look, you have this image on the left with this motorcycle. I want to generate the feature such that this motorcycle will actually turn in front of me. So I want to generate, for instance, this dangerous behavior or this type of event. And sorry, wait, I'm gonna play it. No, it doesn't work. Voila. And so here you see that the video on the right is generated following these rules. So we have a lot of capability to actually then play different scenarios and test our pipeline on it. Here we are actually asking the car on the left to move forward. We can here ask to generate a car that drives next to us. So this is on demand. Here is our other illustration of how we can move objects around. And we can also do it on humans. So when we have this image on the left, we can ask the humans to stay still, to not cross, or cross, and generate how it should look like. It's not perfect yet. We still need to improve the quality by using more data, improving our architecture, maybe our labels. So there's a lot of ongoing work, but this is a very good preliminary result that is motivating us to continue. So there's a lot of hope. Voila. So this is on the first 2 principles, which is basically learning a foundation model in a self-supervised way and using it to have impact in other things. At this stage, we have not yet demonstrated that whatever we have learned here helps us to do the fine downstream task, But this is our next, our ongoing work, and hopefully soon we will be able to demonstrate that. We have also done this for the second pillar, for predicting trajectories. I'm just going to share this link where we showed that if you combine all existing data sets that do vehicle trajectory prediction, for instance, usually this is a field that the industry is helping us a lot, but the industry likes to have their own data in their own format and their own challenge. But we made a lot of engineering work, I would say, to try to unify all these different data sets, challenges, and create a large um, uh, mm, data um, set um, that to run experiments, for instance, across multiple cities. We showed that if you learn, for instance, from 2 or 3 cities, how can you transfer whatever you learn to a new city? How can you be smart in the data? Is more data helping or not? So we can run a lot of experiments cross city thanks to this effort. Then I can look at time. It's I think already 40 minutes. I'm going to potentially go very fast in the remaining ones, but I think in 2-3 minutes I'll be done. The principle of multimodality is basically saying that we have multiple modality that we can take advantage, and one of them is text or the knowledge that we're able to learn from the internet. So this concept of reasoning or looking at rare events, for instance, a kid crossing the street, what if I am able to detect that there is a kid, that there is a ball, but I actually take advantage of what I've learned from internet that will tell me potentially what's happening and will tell me that what the kid will do, so I can take advantage of that to improve my prediction and potentially even understand that this is a dangerous situation and so on. I'm gonna skip that. Also, the principle of residual learning is basically saying that um, we have a tendency to do everything end to end, which is supposing that we want to learn everything from the data, but sometimes we don't need to suppose that. We can say, especially in the context of prediction, look, there are some basic behaviors that I can actually simulate that I know. For instance, the physics. I know that in the context of navigation, I cannot, there is an area that I know that I can navigate, and then another area that is impossible. So within that area, then tell me where I can go. So what you can do, you can say, okay, I'm going to use, for instance, more a knowledge-driven method as a starting point that is based on the physics of my understanding, but I will use a neural network to just correct in some constrained range the output. For instance, in the context of self-driving car, I know that I need to follow the road. So I can say, okay, I know that this is the area that I can navigate, but tell me how in this area I should correct my prediction so that it's aligned with social interaction and so on. So we show that we can do this, and it potentially is a bit more robust. I'm gonna skip this. The principle of causality, basically causality, this is the dream of machine learning. We want to learn causation, but what we learn is correlation. We are aware of that. So how can we become a bit closer to causation? We actually have a few recent papers that we show that, for instance, you can potentially get causal labels. You can say the behavior of my prediction or my prediction depends on this agent and so on. So I can label which agent has a causal impact on me. And you can do this through the term is not coming into my mind, but this causal labeling, you can actually do them in simulation, so you can actually understand with counterfactual experiment where you remove, for instance, an agent in simulation, you see if it has an impact. So you can then label it that this agent has a causal impact on the dynamics, and then use these labels from simulation to train your model and then transfer it in reality to see if you have a positive impact. And then we show that this is actually true. It works. It has a positive impact to get causal labels from simulation and transfer it to reality. And finally, this is my last principle, the principle of in vivo practice. To me, is very interesting because it's a relatively recent field in machine learning, referred to as test time adaptation, test time training. What does it mean is that whatever we learn, for instance, here, um, uh, what we're interested is to develop systems that interact with human. So in biology, when you develop systems that operate in contact to humans, you refer to this as in vivo um, experiment. The opposite is in vitro, where it's more in simulated, in lab setting. So it's more about the theory, but in vivo is really in contact to humans. So you start from in vitro, and then if you're happy with the result, you go in vivo. And I think when we do this autonomous mobility and when we deal with transportation, we are actually in vivo. We are in contact with humans. And human behaviors will not be static in time, and they will change. Like, we already know that they change across cities, but even within the same city, they might change over years. So we cannot suppose that whatever we learn from a city for that city will remain constant over time. So we need to come up with mechanism that will adapt our representation on the fly. Maybe our culture will change. I don't know, the dynamic will change. So how can we have representations and models that can always double check if they're doing a good job, and if there is a bit of a shift, adapt on the fly the representation, um, without necessarily relying on ground truth labeling, but more on self-supervised auxiliary task. So this is the area, and I think this is also very robust. So voila, to sum up, the path to autonomous mobility, AI for transportation and transportation for AI. I think thanks to transportation, we can work on these 7 principles that will impact the pillars of the AI system a bit broadly. And we want to demonstrate that this is true through these different use cases of a self-driving car, autonomous robot, or even autonomous body. Voila, and I'm happy to take some questions. I'm going to share a fun video just for you to laugh. Suppose you have this autonomous vehicle, you see this puddle and this pedestrian. What should the vehicle do? Not that. We can actually hard code that you should always avoid a puddle if there are pedestrians on the side. But that's not good enough, because in some situations, humans want to be splashed. So AI must read humans to make the right decision. And this is my last slide. Thank you. I don't hear anything, but thank you. I don't know if there are some questions.
No, it is.
Yes, I can hear now.
Thank you, Professor. We'll be taking questions from the room now. Yes, Johan.
Thank you so much, Professor. This is really quite interesting research. I do have one question for you. Some people argue that data is noisy and messy for a reason, and that's why it's valuable. So how confident are you that synthetic data can represent ground truth data as well as real data does? Like, how can we make sure that if we train a model on synthetic data and the performance doesn't go well, the reason is that the model is not good instead of the data not being good enough?
I'm not so sure I heard well in the beginning of your question. So maybe You want to summarize the question again, or?
Yeah, but
Much better.
very short question. How confident are we that synthetic data can be as good as real data for training a model?
Okay. Yes, very good question. We are not yet, so we don't know. I mean, there are a lot of even companies that claim that to solve all these problems, they need to create a photorealistic simulator that is as close as possible to the real world. But this is ongoing research. But one way to you can still evaluate that, right? So you can say, look, I've created a photorealistic simulator. I'm gonna train a model on that, but I do have a bit of real data, and I'm gonna see how well I do on real data. So we still have actually a sanity check to see if we are there yet or not. And this is happening in the field. But honestly, over the past weeks and months, the progress in generative AI is so stunning that I think we're not too far from showing that we can generate good data that will actually help train these models. I would say 1 year ago, I would not have the same answer. I would say, oh, we're too far, and we tried it, and there's a huge shift between simulation and real world. But honestly, our last recent experiment, made me rethink this paradigm, and I think yes, soon we can see a lot of benefit from generating synthetic data that is really, really photorealistic, and or even matching potentially your real world distribution. And you see it right online. You see all these amazing success stories. So
Thank you, Professor. We can take one more question from the room if there is any. Okay, we're actually out of time, so we can end the seminar, and it's actually almost 10 p.m. in Switzerland right now. So we're very grateful for Professor Alahi to be able to join us at this late time. Everyone, please join me in thanking Professor.
thank you. And I mean, if you have more questions, feel free to send me emails. I'm happy
Yes.
to.
Yes, thank you so much.
Thank you.